Hello, John. So we have a long question here, and I'm going to try to keep this under the 5 minutes. So I'm going to go kind of quickly here, and it's just kind of go over just the general ideas and how to approach the problem without getting into the answers necessarily. So we are given here, or rather, you're given a vector function, which describes, and I'll use this notation here, which describes the path of a cross-country skier. We're given that the x component is 2 plus x, 6t plus 2 cosine of t. And then the y component we're given is 15 minus t times 1 minus sine of t. And that's the vector we're given. And we're also given the first derivative of the x component, and then we're also given the first derivative of the y component. Now, I didn't double check these derivatives here. I assume if the question gives it to you that it's correct, so we're going to kind of move on from there. So the first question here asks to find the slope of the path at time t equals 4. So this vector valued function here that we're given, this vector here is describing the position, right? And so we want to find the slope of that path, of the position, the path position, if you will, at time t equals 4. So we want to find the slope of this, then we're finding the first derivative. Now, luckily, we are given the first derivative of the y and x components here. To find the slope at that point, what we need to do is evaluate this, of course, at the time that we're given. Now, you may or may not have seen this, but because this essentially is kind of given in a parametric form, because we're given separate x and y components with respect to a parameter t, you may or may not have seen this, but this may look familiar to you. Here to find the derivative if you have a parametrically defined function where each of these are the derivatives of those parametric components here. Luckily, we are given this. So we're given it right here and here. So this is as simple as plugging these into this equation. Straightforward, evaluating, plugging in t, you're done. So for the second part, where it says here to find the time when the position is x equals 60. This is pretty straightforward. So this is literally asking when is the position, this part here, when is that x component, which is right there, equal to 60? Pretty straightforward. Let it equal 60, find t. Done. So moving on to the third one here. We're going to find the acceleration vector when x equals 60. Alrighty then, so of course acceleration is the first derivative of velocity, which is, or otherwise the second derivative of position. We're given the position vector. We're also given the first derivatives here, so it doesn't give us a lot of work to go to get to the second derivative. So we can find the second derivatives here of these things in order to find that, which we would see the second derivative of the position vector, and we can get this vector here, and we'll get some vector, and then we want to find it when x equals 60. Same thing again, plugging this in for x equals 60, finding t for that value, and then going back into that vector, plugging in our found value for t, and that will give us the acceleration vector when x equals 60. Again. Great. So moving on to number 4, let's see. It's asking the speed when the skier is at max height. So if we think about x and y in kind of real space, x is that horizontal component, y is that vertical component. So it's basically asking when is y the highest. And if you're familiar with optimization problems, this is similar to asking, essentially, what is that maximum of that component there, of the y component. So if you're familiar with those optimization problems, we're looking for when the derivative of that y component is 0, because we want that derivative be 0, because that's the top there. So it's a matter of finding out when is the first derivative of that position vector of the y component of the position vector 0. Now, of course, if they're at max height, The assumption usually in this case is that the speed is, of course, going to be only in the x direction, so you don't have to worry about finding weird, lengths of vectors in this case. But yeah, so then you can just find out the velocity in the x direction when that y component is 0. And lastly, for number 5, we're asked total distance in meters traveled. I mean, this can mean a couple things, but I'm pretty sure it means, since it's a cross-country skier, it means the actual length traveled. So in this case, it would be the length of that curve that we're imagining if we're tracing the path as a curve. In this case, you may be familiar with this. There is essentially an equation that you can use to solve this, which is the integral from some time to the next of the square root of this plus this here. And in this case here, lucky again for us, we're actually given these as well. So that's this here. That's with respect to time. So we're given that x with respect to time, and we're given that y with respect to time. So this gives us the tools we need, and it is pretty straightforward, plug and chug, if you will, to get that answer. Again, like I said before, and I've gone over time, of course, but as I said before, this is a big question with a lot of parts, so I just kind of went through the basics of how to approach it. So let me know if you have more questions. Thanks and good luck.